Howdy, my name is Ethan Weber, and in this video I will be presenting work performed by myself and my co-author Amy Haft on characterizing field emissions in electrostatic tractor operations for geosynchronous orbit debris removal. For a brief overview, the electrostatic tractor concept is a contactless method for active debris removal in geosynchronous orbits, and this concept works by using an electron beam on board a servicing spacecraft to induce differential charging between the surfacer and a target debris object. Now, as electrons leave the surfacer and impact the target charges negatively while the surfacer spacecraft charges positively, and this charging creates an electric potential difference between the spacecraft, resulting in an attractive electrostatic force that allows the surfacer spacecraft to tow the target debris to a graveyard orbit. The main advantage of this method over other ADR solutions is that it's touchless, meaning that it can be used regardless of if a debris object is tumbling, and this makes it especially useful in geosynchronous orbits, where debris spin rates of up to tens of degrees per second have been measured. Furthermore, around 90% of insured spacecraft are in geosynchronous orbits, and approximately 50% of geosynchronous satellites were found to be non-compliant with IADC debris removal regulations at the end of their life during a study between 1997 and 2013. Now, for a little bit more background on the electrostatic tractor concept, it was originally proposed with a continuous electron beam, meaning that there's a continuous flow of electrons streaming from the surfacer to the target debris object. But in recent work performed by my co-author, it has been found that the attractive force between the surfacer and target found through this differential charging can be increased by pulsing the electron beam instead. This method involves changing the duty cycle of the electron beam, which is the ratio between the time the electron beam is on or off, while keeping the electron beam power constant. Then, if you optimize this duty cycle to maximize the electric potential difference between the surfacer and the target, the force between the spacecraft can be maximized. And when you do maximize this force, you can reduce deorbit times from hundreds of days with the continuous beam down to as low as 5 days using the pulsed beam under optimal conditions. Now, this shows that the pulsed electron beam is a promising method to improve the efficiency of the electrostatic tractor concept. But if we look at the top two plots, we can see that this increase in force corresponds to a greatly increased electric potential difference between the target and surfacer on the order of hundreds of kilovolts. Now, this significant increase in electric potential has an added risk, which is a phenomenon known as the field electron emission. Now, field electron emissions, also known as field emissions, are a phenomena in which electrons escape the bonds of a material when they are excited by a strong electric field. And this is modeled using a modified form of the Fowler-Nordheim equation, which is shown at the bottom of the slide. And if we look at this equation, we can see that the field emission current density, which is shown in J, is almost solely dependent on the surface electric field magnitude, which is also directly affected by the electric potential between the target spacecraft and surfacer spacecraft. But why does this matter for the electrostatic tractor concept? Well, if you think about it this way, field emissions represent a current of electrons that are leaving the target spacecraft. And if this current is high, the electric potential between the target and the surfacer decreases. And that reduces the attractive force produced between the two spacecraft. And as such, we want to understand what impacts these field emissions, what makes them greater or lesser. And also we want to understand how these field emissions ultimately impact the efficiency of the proposed pulsed electrostatic tractor method. To recap, past research has shown that using a pulsed electron beam can greatly improve the performance of the electrostatic tractor concept, and it does this by greatly increasing the intercraft electric potential difference. But this also introduces the risk of field emissions. Now, this gives us two questions that we want to answer. Firstly, how do target geometry and proximity to a servicing spacecraft impact field emissions on a target spacecraft? And what are the effects of these field emissions on the efficiency of the pulsed electrostatic tractor concept? To answer the first question, we start by looking at how geometry and electric potential impact field emissions for an isolated spacecraft. Now, spacecraft design guidelines generally suggest that a spacecraft should be fully conducting across all of its components, and as such, the charges spread across the spacecraft until an electrostatic equilibrium is reached. Now, because of this, charge density tends to be highest at these sharp points on a spacecraft, and these are points with low radius of curvature. And this results in a greater surface electric field at these points, and thus a greater risk for field emissions. For a spacecraft, these points tend to be antennas, sharp corners, and edges, as well as sharp surface features like surface asperities, torn mylar blankets, or tin whiskers. And because the strongest surface electric fields tend to be at these sharp corners, we can narrow our first question of how the geometry impacts field emissions down to how the radius of curvature of sharp features on a spacecraft impact field emissions. To answer this new question, we turn to computational simulations, and we start by reducing the spacecraft to just that sharp surface feature and model this feature as a sphere in COMSOL, which is a multi-purpose physics simulation tool. And using COMSOL, we can perform a parametric study using stationary simulations, which are non-time varying, to find the surface electric field magnitude for surface feature radii ranging from 1 micrometer up to 0.5 millimeter. And then we do this for a variety of duty cycles ranging from 0.01, which means that it's the electron beam is pulsing for only 1% of its runtime, up to 0.1, meaning 10%. And this duty cycle gives us voltages. From the surface electric field that we calculate from the simulation, though, the field emission current density can be calculated using the Fowler-Nordheim equation from before. So from these simulations, the following results are found. The plot on the left shows the log 10 of the surface electric field magnitude for the aforementioned radii and duty cycles, and the plot on the right shows the log 10 of field emissions for the same variables. And from these plots, we can see that the surface feature radius has a significant impact on both surface electric field and field emission current density, much more so than the duty cycle. So across all voltages, we see that having a smaller radius really greatly increases the surface electric field and the field emission current density. Now, specifically looking at the plot on the left, we actually see that there is a super exponential increase as the radius decreases. But despite this, if we look at the values on the z-axis of the right plot, we can note that the field emission current density is very low for most radii. It only reaches around 1 amp for radii below 0.06 millimeters, and that's only for the optimal duty cycle that has the largest potential difference between the two spacecraft. Now, these results give us insights into the geometric impacts for an isolated spacecraft, but when we have real electrostatic tractor operations, we also need to consider the effects of the presence of a servicer spacecraft. For a quick recap, we start with our isolated spacecraft, but when we have the electrostatic tractor concept, the target spacecraft is negatively charged and the servicer spacecraft is positively charged and is working in close proximity to this target spacecraft. Now, when the positively charged spacecraft comes into closer proximity with that target spacecraft, the electrons in the target spacecraft redistribute and generally move closer to the positively charged spacecraft in order to reach that electrostatic equilibrium. Now, this collection of charges near the servicer can result in an increase in the electron density and the sharp points discussed earlier. And this, again, enhances the surface electric field at these points and brings us to a new question. How does the separation distance between the target and the servicer spacecraft increase or impact the field emission current density? To answer this question, we once again turn to using stationary computational FEA simulations and the Fowler-Nordheim equation like before. But for this study, we add in a 0.5 meter radius positively charged spherical servicer. Now, for the study, the target feature radius is varied between 5 micrometers and 0.1 millimeters, and the separation distance between the servicer and target feature is varied between 1 centimeter and 2 meters. Now, instead of varying the duty cycle like we did with the isolated spacecraft, we're just going to look at the potential difference that is from the optimal duty cycle, which corresponds to the largest potential difference between the target and the servicer. And this gives us a worst case scenario. And the results of this study are very reminiscent of those that we saw for the isolated spacecraft. The plots look very similar, even though we have different variables. The plot on the left in this case is once again the log 10 of the surface E field. The plot on the right is the log 10 of the field emission current density. And this time we have target tip radius and separation distance rather than having the duty cycle. Now, when we look at these plots, it almost appears that the separation distance has no impact on either the surface electric field or the field emission current density, but this is actually not the case. Analytically, we know that that can't be the case. And when we zoom in, just looking at the surface E field, we do see a super exponential increase with separation distance, but this is much smaller than what we see for the target tip radius. Over a change between 1 centimeter to 1 meter, we only see an increase of around 0.5 or 0.05 order of magnitude, so 10 to the 0.05. And meanwhile, when we look at the target tip radius, we see multiple orders of magnitude increase. So really what this is telling us is that separation distance is much less impactful than the feature radius. And so far, these results have been found using stationary simulations, as I said before. And once again, stationary simulations are not time varying. And while this gives us good insights into the impacts of geometry and separation distance on field emissions, time-varying charging simulations are needed to really determine how these field emissions impact the effectiveness of the pulsed electrostatic tractor. In the real world, when we have real spacecraft charging, we don't instantly start at some electric potential difference. We have to reach that starting from around neutral. So we are trying to simulate that actual change and see if we actually reach these potentials that we found in past studies to really see if field emissions are even a problem or if we're not able to reach the previously found voltages. So to explore this, we model the time-varying effects using the AVS Labs in-house charging code. Now, in this model that we've created in the in-house charging code, we use a spherical surfacer that has a radius of 1.5 meters and a 4-meter radius spherical target that has a small surface feature, and we vary the radius of that surface feature. And the surface electric field is then calculated analytically using the equation shown below, and this equation is derived in further detail in our paper. And our paper also shows that this equation matches pretty closely to the results from COMSOL. And then this surface electric field is then used in conjunction with the Fowler-Nordheim equation from before to find the field emission current density. So from these simulations, we find the following time-varying results. If we look at the top left plot, this shows the target potential over time for varying radii. And we can see that as we decrease the radius of curvature of that surface feature on the target potential is decreased, or the magnitude of the target potential decreases significantly, down from around over 150 kilovolts down to around 25 kilovolts. And we see a similar effect looking at the top right plot for the surfacer potential. That also greatly decreases and actually goes negative for a short period due to the surfacer reabsorbing the field emissions from that target spacecraft. And overall, this results in a decrease in the potential difference between the two spacecraft and therefore a decreased force. And this suggests that the improvements gained from using the pulsed electron beam may be greatly diminished by field emissions if the target spacecraft has small surface features. Now, despite this is only really the case for small surface features. If we look again at both these plots, for the green curve, which represents a surface feature of 50 micrometers in curvature, we see that this green line is basically the same as field emissions not existing for the simulation. So we would assume then that any radii that are greater than 50 micrometers would not have any notable effects. So we would still see improvements for any target spacecraft that do not have features below that 50 micrometer cutoff. Another thing to note, and this is talked about more in our paper, is the current density shown in the bottom left does not reach the arcing criteria. In this case, we use the vacuum breakdown criteria of 10 to the 12 amps per meter squared. And if you look at that plot in the bottom left, the maximum current density for all radii does not reach 10 to the negative 11 amps per meter squared. And this is because for these smaller radii where we're more likely to have field emissions for lower potentials, we never actually reach the high potentials where we would have high field emission currents. So there's basically a cutoff at around 10 to the negative 11 amps per meter squared for this time varying case. And that suggests that we shouldn't have to worry about arcing due to field emissions. Now, this brings us to the conclusions. We modeled both a small surface feature isolated and in the presence of surfacer spacecraft using COMSOL, and the results of these simulations showed that a target spacecraft surface feature radius, a target spacecraft's surface feature radius of curvature has a notably greater impact on the field emission current density than separation distance. And both of these studies, both the isolated and the study with the surfacer spacecraft, use simplified models. And in the future, we would like to look at higher order modeling that use more complex geometry or full-on spacecraft models. And then we also looked at time-varying results with a more simplified charging equation. And from these, we found that the field emissions do have the potential to greatly reduce the effectiveness of the pulsed electrostatic tractor concept compared to previous studies that didn't consider field emissions. But these effects are only notable for targets with sharp features or features that have radius of curvature below around 50 micrometers. And we haven't fully compared these results to the originally proposed continuous electron beam, but that is the next step that we are currently pursuing. And then finally, the time-varying charging study also showed that arcing from field emissions is not expected. With that, I'd like to conclude my presentation. Thank you for watching, and if you have any questions, please feel free to reach out to myself or my co-author at the email addresses listed on this slide. Thank you again.